Hello, my quarantine kids. I'm going to run through this molecular geometry Vespers theory stuff with you and stuff you need to know for the quiz tomorrow. If you are quarantined, I will be sending you the quiz, and you're going to use the honor system and send it back to me. If you're just homesick, you'll take it when you get back to school the next day. So let's see. Um, Molecular geometry Vespers theory. A couple of things I just wanted to reiterate before the quiz tomorrow, and I think we talked about this last week, but a single bond, so if you just have a single bond, that's a sigma bond, okay? If you have a double bond, you have one sigma, one pi bond. If you have a triple bond, you have one sigma bond and two pi bonds, all right? So that's something to remember. Something else, a single bond is the longest bond, and it's also the weakest bond. So if you have Cl, you've got your single bond there, and it's a relatively weak bond. It's a long bond. There's a lot of space between them. I think of like Red Rover, if you guys ever played that. If you hold your arms like straight out and hold on to the other person, it's real easy to run through them and break that bond. However, if you have a triple bond, like with two ends here, it's a short bond. So you're holding hands closer if it's Red Rover, and it's really hard for people to run through them and break that bond. So the shorter bond is stronger, and that's a triple bond. So just a couple things to know for your quiz. Um, okay, talking about molecular geometry, Lewis structures are two-dimensional. So we've been doing Lewis structures, but molecules are actually three-dimensional. Think about like if I draw a picture of you as a stick figure, that's just a two-dimensional picture of you. But you are a three-dimensional human being. So in order to draw something that represents a three-dimensional compound, we use molecular geometry. We use something called the Vesper theory. The first thing to know is that all molecules that only have two atoms in it have a linear shape. So HCl here would just have a linear shape. Anything after two atoms, we need to use the Vesper theory for. And this is what you guys did on the POGL yesterday. So you should have a pretty good feeling about how this works. So Vesper stands for valence shell electron pair repulsion. It's basically saying electrons repel each other. We know that. They're all negative, so they repel each other. We use this theory to predict the shapes of molecules with more than two atoms. That's our molecular geometry. So electrons, both bonded and unshared pairs, repel each other. The electron pairs will be as far as possible apart as possible. So I showed them in class, if you have two balloons and you tie them together, what they do is they end up like hanging out in a figure eight type of shape. So they're pushing each other away. So they wouldn't hang out like this if you have two balloons together. They hang out like this and push each other away. That's what happens when electrons repel each other, and they form these molecular shapes. Hybridization is a vocab word. It's a process in which atomic orbitals mix and form new identical hybrid orbitals. So hybrid, of course, is a mix. It sounds difficult, but it's actually really easy, and I'll show you in the next slide how we deal with this. But for example, carbon's valence energy level. So if you look at the periodic table, carbon is an energy level 2. In energy level 2, we have 2s, and then we have 2p. Well, carbon is hanging out in 2p. It's actually 2p2. But p has 3 orbitals. We know that. S has its 1 orbital. So what happens is when it bonds, this hybridization occurs, and what it does is it forms these 4 identical hybrid orbitals that are called sp3. So we'll talk more about that in just a second. All right, what we want to do here is we want to fill in this chart together. I'm going to cross out that because I'm just going to write Lewis structure here because we need to draw our Lewis structures first. So you guys can do it like this, okay? So let's talk about carbon dioxide first. All right, you guys know how to draw your Lewis structures. This is why we built from drawing Lewis structures. So if we are drawing carbon dioxide, remember you need to do your required, carbon dioxide is CO2. Each carbon needs 8, each oxygen needs 8, so that's a total of 24 required available valence electrons. Carbon has 4. Oops, carbon has 4. Let me draw that. Each of the oxygens have 6, so that's 12, 16. So then we take that, subtract, we get 8 divided by 2 equals 4 bonds. So you need to be able to draw your Lewis structures. So since we need 4 bonds, we're going to have double bonds on the O's. Here's my valence electrons to finish out those O's and make them stable. Those aren't bonds, those are dots. It just wants draw dots, sorry. So we need to look at the number of atoms bonded to the central atom. So this is how many bonded domains. All right, so we have one area here where there's a bond, or it's a double bond. It doesn't matter if it's single, double, or triple. That's just one domain. And we're only looking off of the central atom. Then we have another bonded area here. So what we have is we have 2 bonded domains. Now we need to look at the central atom and see if there are any lone pairs on it or unshared pairs on it. There are not. So we have 0 unshared pairs. If we have a compound with 2 bonded domains and 0 unshared pairs on the central atom, that means it's linear. So when we draw a picture of what that would look like, as if we're just drawing our, it's going to be hard to draw this way, I can tell. Here is what linear, here's what linear looks like. So make sure you draw the linear shape somewhere. I didn't leave a space for it, so you just draw it there. I'll erase all this so I can draw it out here after this. Actually, let me just draw it out here. That's easier. Let me use this instead. All right, so this is what linear looks like when we're talking molecular geometry. Now let's talk about its hybridization. Since we have 2 domains, all we do is we always call the first domain S, and then any domain after that is going to be P. So third domain would be P, fourth domain would be P, so on and so forth, okay? So what we have, since we have 2 domains, we have an S and a P. So our hybridization is simply SP right there. Let's look at CH2O. I'm not going to go through how to draw all of these Lewis structures with you because you definitely should know that by now. So here's CH, and it's going to be a double bond on the O. And that's our Lewis structures for CH2O. So now that we have the Lewis structure, now we can see how many bonded domains we have. I see 3 bonded domains. There's one area here, there's another one here, and there's another one there. So we have 3 bonded domains. We have 0 non-bonded domains on the central atom, which is carbon. When we have 3 bonded domains and 0 non-bonded domains, that means we have trigonal planar. So trigonal planar looks something like this. Again, I'm just not great at drawing these, but I'll give it my best shot. Let me try it again. Okay. And it looks something like that. That's what trigonal planar looks like. All right. You guys are not responsible. The one thing you don't have to know is you don't have to know the bond angles, whether they're 90 or 120 degrees, whatever. You don't have to know those. All right, it's hybridization. We have 3 domains total. First domain is S. The next 2 domains out of those 3 are P, so we call that sp2. Let's look at carbon tetrahydride. Carbon tetrahydride. Is drawn like this. All right, so what I see around the central atom is I see 4 bonded domains, 0 non-bonded domains. So if we have 4 bonded, 0 non-bonded, it's tetrahedral. Remember, tetra means 4, so that one's kind of easy to remember. Looking at how this looks as a picture. Put your central atom there, and then you've got, oh goodness. Okay, central atom. This guy, this guy, this guy, this guy. They often draw this as like this triangular type thing to show that it's behind it, but it's fine. As long as you draw it like this, I'm fine, because I'm terrible at drawing these three-dimensional shapes. All right, as far as its hybridization, we have 4 total domains. Again, the first one's always going to be S, second P, third P, fourth P, so we have 3 Ps, so sp3 is our hybridization. All right, we've got water. This is water's Lewis structure. Ugh, doesn't like me to draw my dots. It's going to have to because I need them. Okay. All right, so those are my dots. They're my unshared pairs. So what I've got with my central atom here is I have 2 bonded domains, one between the O and HH. I also have 2 unbonded domains, so I have 2 unshared pairs on the central atom. If I have 2 unbonded and 2 bonded, that means that my shape is bent. Bent looks like this. Why is this so hard to draw? Let me try it like this, sorry. Okay, here's my, oh my gosh. Here's my central atom, whatever. Then I've got, hold on. Sorry guys, let me get this out of the way. Maybe I just need a little more room. Let me try this again. Okay, so here's my central atom. All right, here is my first unshared pair. I'm just going to have to keep redrawing that central atom. Here's another unshared pair. There is obviously a better picture in your POGL. Here's the bonded, and this one's bonded. Something like that. So those unshared pairs are kind of in bubbles there. So that is your bent shape. As far as your hybridization, you have 2, 4, so you have 4 total. So that means 1s, 3 Ps. All right, last one, ammonia. Ammonia is NH3. That's that one I've asked you guys. Oh no, that one's on your Chem Cruncher. It's my H. And then I've got my unshared pair here. So looking at this, hopefully you can still see that little dot. It's there. Okay, so looking at this, I have 3 bonded domains. I have 1 unbonded domain or unshared pair. So this is going to be pyramidal. Sometimes it's called trigonal pyramidal. As long as you see the word pyramidal, you know it's this one. So looking at what that looks like, we've got our central atom here. And then we've got our, unshared pair up here. Good Lord. And then we've got our 3 there's your central. So kind of looks like a weird little octopus with only 3 legs or something. As far as your hybridization, again, you have 4 total domains. So it's going to be S, and the next 3 are P. And there you have it. So hopefully that makes sense. I do need to still talk to you guys about the polarity. Okay, so we have polar molecules. We already talked about polar bonds. That's when you have, remember, your electronegativity differences. So you have nonpolar covalent if it's less than 0.3. If it's between 0.3 and 1.7, the electronegativity. oh my goodness, electronegativity difference. You have polar covalent, and if it's larger than 1.7 electronegativity difference, you have ionic. Remember, you got to memorize that, okay? So if you can look at bonds and tell their electronegativity difference and whether they're nonpolar, polar, or ionic. We got to talk about looking at entire molecules. So molecules with a partial positive and partial negative end, or pole, are polar molecules. They have to contain at least one polar bond. So H2O is a good example of this. So we have our O, we've got our H's here. There's my unchaired pairs. All right, if we look, O has an electronegativity value. If you look at your periodic table, your pink one, your Chem Cruncher, on the periodic table side, if you look at O, under the 16, there's a little number that says 3.5. That's its electronegativity, okay? Hydrogen's electronegativity is 2.1. So for this hydrogen-oxygen bond right here, we have an electronegativity difference of 1.4. That puts it right into the polar bond category. So this is a polar bond. So remember, if we're looking at that bond between hydrogen and oxygen, that means that the electrons, since oxygen has a 3.5, it's more electronegative, those electrons are going to hang out closer to the oxygen, making it partially negative. Those electrons are not hanging out as close to the hydrogen, so that leaves it with a partial positive charge. Same thing happens with the other hydrogen. It gets a partial positive charge because those electrons are hanging out closer to the oxygen. So we're left with a negative polar end and positive ends. So that means this is a polar molecule. For nonpolar molecules, they don't have a distinct positive or negative end. They contain either only nonpolar bonds. For example, if we had Br2, Br and Br, our Br and Br have the same exact electronegativity because they're both the same element. So you have a 0 electronegativity difference, making it nonpolar covalent. That's the only bond in here, so that means that this whole molecule is nonpolar covalent. Okay, so if all the bonds are nonpolar covalent, it's automatically a nonpolar covalent molecule. You might have something like CH4. All right, carbon has a 2.5 electronegativity. Hydrogen has 2.1. So your difference is 0.4. That puts it as polar covalent. So this bond right here is a polar covalent bond in which the carbon would be slightly positive and the hydrogen would be slightly negative. This bond is polar covalent. This bond is polar covalent. And this bond is polar covalent. So what you have is you have all polar covalent bonds in here. However, because this is a symmetrical shape here, so you've got these H's on each side, the carbon is pulling equally on the electrons of each H. So what happens here is that the whole molecule, because it's symmetrical, is going to be non-polar covalent, even though it contains polar bonds. So a good way to tell if it's non-polar covalent if it is symmetrical. So if it's linear, and often if it's tetrahedral, it's going to be a non-polar covalent molecule. Generally something that is not, so let's say NH3, so if you have your N, and if you draw it like NH3 is pyramidal, so it's going to be drawn something like this. So that's its molecular geometry. You can tell it's not symmetrical, okay? You've got a lone pair over here. You've got these H's in different directions down here. So it's not symmetrical. So this would be polar covalent. So that's just one way to tell. I think that's all there was. Let me just